recording. Okay, it's great pleasure to have the Sung-Soo Kim from the Chengdu. He's going to tell us about the bootstrapping BPS spectra of 5D6 SQFT.
Okay, thank you for the introduction and thank you for the invitation. Okay, so today I will talk about the bootstrapping BPS spectra of 5D and 6D super quantum field theories. This work is based on this paper in collaboration with Untitled Kim. I think he's now here, and Sung-Soo Kim and Ki-Hong Lee. And another related paper is 1908 paper, the collaboration with Junho Kim and Ki-Hong Lee and Kim-Young Lee and Jae-Won Song. So in this talk, we will discuss 5D and 6D field theories, but probably I will mainly focus on 5D aspect, 5D field theories. In particular, I will be talking about how to obtain the BPS spectrum of the 5D series. BPS spectrum here, I mean a Nekrasov partition function or partition function on alpha cross S1 in the omega background. So I think in the, sorry. In this audience, probably we don't need much of introduction, but nevertheless, let me say that the field is very rich and there has been lots of researches. In particular, there's a lot of attempts and studies and systematic way of obtaining this Nekrasov partition function, and some of which is known as ADHM construction, and also topological vertex, or DIM algebras. I mean, each of them is very successful and then computes the 5D series, 6D series with the various meta contents, engaging groups. However, it also has some limitations and challenges, which includes exceptional gauge group is particularly difficult to find the ADHM construction and topological vertex, etc., etc. But although the G2 has a very successful getting this ADHM constructions, also topological vertex as well. When adding the matter, it became much complicated and difficult to evaluate. In particular, if we have a higher dimensional representation, is much difficult. Also, higher transformer level is also very notorious. And many of the theories also can be seen as a five-brain web, but although we have a large amount of or large class of theories that can be presented by five-brain web, we still have many theories that doesn't have a five-brain webs. So etc., etc. These are the limitations. In this talk, I will talk about yet another powerful way, which turns out to be very powerful way of computing Nekrasov partition function. And this is a celebrated Nakajima-Yoshioka blow equation. We already have several talks about this this topic, Nakajima-Yoshioka blow equations. And for example, last one is Kai-Won showed that the very beautiful talk about this blow equation. In this talk, we devised a complete blow-up formulation, which enables us to compute the BPS spectrum of any supersymmetric gauge series, which has the UV completion in 5D and 6D. So I like to emphasize that this is the any. So it doesn't matter whether we have a exceptional gauge groups or matters with matters in higher representations, others. So I think I'd like to convey some idea that this method can be applicable to any supersymmetric gauge series in 5 dimensions and 6 dimensions. Although I do not compute all of them, I compute some representative theories. By the way, if you have some question, please interrupt me. It will be much easier for me to interact. Okay, so let me start with this, what I mean by n equal 1 super conformal field series in 5 dimensions. And it has the A supercharges. It also has the SU2R symmetries. The particle content is, so it has a vector multiplet, which consists of the gauge field A mu and scalar field phi, which is the real scalar. So there's a one with a one real scalar in the vector multiplet, and it's a super partner. And there is also hypermultiplet, which is made up of 4 real scalars or 2 complex scalars in the representation of doublet in the R symmetry representation. And then if we look at a vacuum moduli space, then we have 2 distinctive branches, the Coulomb branch and Higgs branches. The Coulomb branch is parameterized by the vacuum expectation value of scalars in the vector multiplet, while the Higgs branch is parameterized by the scalars in the hypermultiplets. In particular, in the Coulomb branch, gauge group is completely broken to U1 to the rank of the gauge group. There, a W boson mass is obtained as a root times this phi, which is the scalars in the vector multiplet, and hypermultiplet mass is given as a weight, which is the representation that the pi hypermultiplet lies, and with the mass of a hypermultiplet. Here in 5 dimensions, we have also a U1 topological symmetry, which is associated with instanton. This instanton plays a very important role in the UV limit. If there is a fixed point, and it we encounter that there is a global symmetry enhanced from the portable tip to symmetry times U1, this topological, to the bigger one. And G is a coupling of the theory taking infinite limit, and many theories have a fixed point. So we have a superconformal series. Or although we may not have the gauge theory description, but we may have the fixed point theory. But in that case, the low energy theory is just a mass deformation of this superconformal field series. Along the Coulomb branch, the theory is described by the low energy effective theory or low energy effective action, which is characterized by the prepotential. This is potential F is cubic. It is given as this way. So this is more like a classical term, and this comes, the second half is coming from one loop determinant. So let me talk about this one first. This is a vector contribution, and this is a hypermultiplet contributions. And as these are given as a absolute value, the Coulomb branch is divided into a distinct subchambers or phases. Depending on these phases, we may have different expressions given the same theories. And this first part, this MA is simply, I have in mind that it's a quiver theory. So for the time being, we can imagine that this A is 1. And then I runs from the ij runs from the rank of the gauge group. So here M is basically the Bayer coupling. And then in the Coulomb branch, we can compute the, we can take a second derivative on this prepotential with respect to the scalars. And that actually gives the effective coupling. That it plays a role of the Coulomb branch metric. Here is a killing form of the gauge group. Here kappa is a Chern-Simon, classical Chern-Simon level. And D is made out of the totally symmetric operator in terms of the generated subgroup. And here Chern-Simon action we can obtain in this way. And then taking triple derivative on this prepotential and give rise to effective Chern-Simon level. Okay, effective action also contains a mixed gauge and gravitational Chern-Simon terms, which is given, takes this form. Here, A is a gauge field, and P1 of P is a Pontryagin class of tangent bundle of the 5D spacetime T. And then the coefficient here is can be obtained in this way. Here the vector contribution, and this is again this hypermultiply contributions. There's another this mixed Chern-Simon term, which is the mixed gauge and SU2R symmetry Chern-Simon term. It also takes a form in this form. So here C2 of R is the second Chern class of SU2R symmetry bundle. And the coefficient is having this on vector contribution only. It is because of the hypermultiply is singlet on the fermions in the hypermultiply is singlet on the SU2R symmetry, and we only contribute a vector in the gauge genus. And more importantly, if we take the Dynkin basis, then this always turns out to be always 2. So although we have some Coulomb branch, this effective action, if theory is given, these are all automatically given. So as we are talking about the partition function in the omega background, here what I mean by partition function is a Witten index counting BPS state, the state which is annihilated by the supercharged Q and Q dagger. And this one takes this following form, where is 1 to the minus the fermion number operator. And then J1 and J2 are SO4 generators. J of R is SU2R symmetry, and phi is the Gauss of the gauge group vector multiplied, and H is the Gauss for the hypermultiplets. And then it is known that the partition function is factorized in a form that is the perturbative and instanton. And perturbative also include the classical part and the one contribution, which takes the in particular perturbative part is well known of having this form. Here the P1 and P2 is the associated with maybe fugacity associated with the omega deformation parameters. And it's the W is weight of the matter it belongs to. And here the Z classical is the E epsilon, which I will talk about soon. And the Z instanton part is just the expansion of the instantons. So here, the E, which I am going to call effective potential, which is evaluated given this effective action of the Chern-Simon and then mixed Chern-Simon, the gauge and gravity and gauge and R symmetry and their superpartners. And then evaluated on this, we get the following expression, which is the prepotential that we discussed. And these are the two contributions. And then this in the given theory, we take this value. This effective potential will play a very important role in computing the BPS spectrums, which I will also emphasize later when it appears. Okay, so this 5D theory can be also seen from the geometric engineering. So M theory on a shrinkable Calabi-Yau 3 can engineer 5D superconformal theories. So shrinkable means that all holomorphic surfaces shrink to a point or non-compact to cycles. The singular limit of the Calabi-Yau 3 actually is guarantees that there is a superconformal theories at the singularities. This Calabi-Yau 3 can be kept with this Hertzsprung surface Fn and P2. And Fn is the Hertzsprung surface of the base degree n, and these are the complex two-dimensional complex surfaces. And these are the building blocks of the basically the shrinkable Calabi-Yaus. And by gluing these Hertzsprung surfaces and also together with their blowup, we can construct the 5D theories. For example, the theories like known as Egio theory or local P2 is this one, or F1, or correspond to SU2 with the Chern-Simon discrete zeta 0, and F1 surface correspond to SU2 with the Chern-Simon level discrete zeta pi, F2 discrete zeta 2 pi. If we glue to F1, we get SU3, and gluing in the different Hertzsprung surface, we generate SU3 theory with a different Chern-Simon level. So basically, there's a gauge theory and there's a corresponding geometry. So let me make a comment on this, the correspondence. Coulomb branch is corresponding to a Kähler comb of the Calabi-Yau 3, and then where the volume of all the two cycles, holomorphic cycles, is positive. And then Coulomb branch parameter. Sorry that my voice is a little bit weak today. Coulomb branch parameter is the Kähler parameter for the compact surface Ci or the divisor. And then flavor mass is the Kähler parameter for non-compact surface divisors. Okay, the BPS space, BPS state. I'm very sorry that let me drink water.
Take your time.
I think I'm not fully recovered from the. Yeah, okay.
I can see that. So take your time.
Anyway, this BPS state is basically the M2 branes wrapping these two cycles. The particle mass is basically the volume of the cycles. And we earlier said that there's a mixed Chern-Simons level, and basically the cubic Chern-Simons level is associated with the triple intersection numbers. And the DI is, as I said, this is divisors of the complex four cycles. Oh, it doesn't have to be called four cycles, compact. And the mixed gauge gravitational Chern-Simons coefficient can be the intersection of the DI with the second Chern class of the Chern-Simons, Calabi-Yau 3, which is given as this. And the surfaces that we know, they take these values. So as they are taking this value, if we know their geometry, we can basically compute these. And also the mixed gauge R-symmetry Chern-Simons level, as I said before, it will be 2. So then let me discuss with all these ingredients.
So I have a question.
Yes.
For the non-compact Calabi-Yau, can you calculate the second Chern class? I thought it's not a well-defined quantity.
Actually, I don't know.
Okay.
No.
Okay, fine. Thanks. I just wonder that when you talk about these mixed gauge and gravitational and Chern-Simons term, somehow you should involve at least the compact Calabi-Yau, because you are talking about gravity theory, and for a compact Calabi-Yau, there's no notion of this shrinkable Calabi-Yau.
Can I add some comments about it? Yeah. So we can compute this second Chern class. Oh, sorry. This mixed Chern-Simons coefficient for the non-compact Calabi-Yau cases, but this number can be computed only for the compact surfaces embedded in the non-compact Calabi-Yau 3.
Can you say again? You calculate second Chern class of Calabi-Yau by identifying with some compact surface inside of that?
Yeah, so non-compact Calabi-Yau 3-fold embeds some compact surfaces, complex surfaces like the P2 or blown up of Hertzberg surfaces. For such surfaces, we can compute this intersection of the divisor with the second Chern class of the Calabi-Yau 3.
Okay.
But you cannot compute this number for non-compact surfaces.
Yeah. That's what in my mind. Okay. Thanks.
So let me briefly review this the blow-up equation. So we're talking we are interested in the partition functions C2 times S1, and when we say the blow-up, we meant the origin of C2 is replaced by a P1. Here, this is a P1, for example. And then this is a blown up geometry of C2. As you know, a P1 has 2 fixed points, and north pole and south pole. And then localization computation can apply here at the fixed points. And then partition function, basically we can have the on the north pole and south pole. So before applying blow up, we have a partition function that we are interested in computing. Then after that, after the blow up, we can have the this factorized partition function at the north pole and south pole. And even on P1, we can turn on a magnetic flux associated with the gauge symmetry and flavor symmetry, which I denote by N and B. And then we sum up all these magnetic fluxes. And then this blow-up procedure is a smooth procedure, so we can blow down. And then the before and after theory should give the same. Therefore, it gives rise to a very non-trivial recursive relation of the partition function. Therefore, if we have the for example, if I have the background magnetic fluxes, if we turn on the different background fluxes, let's say 3, and then we will have the three different recursive relation with the 3 unknowns, which is this, and this, and this. Basically, this gives a hope that we can fix the partition functions. The more systematically, I think the idea is this, and then with all the fluxes and then all epsilon parameters and the north pole and south pole and their shift are taken into account. This Koteshu and Nakajima-Yoshioka's blow equation can be given as this equation. Here, these the chemical potentials appearing this here. These are the shifted because of the magnetic fluxes, because they are giving the sort of the angular momentum, shifted angular momentum, and they are giving this shift. But also, this lambda is can be which actually doesn't depend on the dynamical parameters. It can be either 0 or non-zero. If it is non-zero, it's known as unitary blow equation. If it is a 0, and this is called a vanishing equation. And along this Nakajima-Yoshioka blow equation, there has been lots of studies and generalizations, starting from this 5D, 45D SUN Suho-Yang mills in the initial papers and their generalizations. Also, exceptional gauge group is also included, and also meta contents, and also in this direction is also generalized. And then local Calabi-Yau generalization was done these people, and also further extended to the elliptic case, or 60 cases with various papers. And very recently, 62,0 theory or 5D n equal 1 mass deformed theory also systematically also considered in these papers. And the last talk by Kai-Wan also considered the RG flows and dualities and global symmetries, and also possibly classifications. There has been lots of the studies along this blow equation. Today, what I am going to talk about is that partition function Z on the omega background of the any n equal 1 gauge theory can be computed by the blow equation with the following inputs. Here, one input is effective prepotential that I discussed earlier, which is given if theory is if we are interested in a certain theories, we can consistently obtain. Another one is a magnetic flux, which is important. What kind of magnetic flux is allowed, is not allowed, is another input, which we will also discuss shortly, and up to some flux transition. With these two inputs, our claim is that any theories can be computed. So the partition function, here the effective potential we already discussed. Let me make another comment. The partition function here we meant, here we have given as an effective prepotential. Also, the partition function takes the form of the compactified buffer invariant. Effective potential, prepotential we already discussed. This Z GB is a refined compactified buffer invariant of the following form. Here the PE is a plasticity exponent, and the JLJR is the charges of the SO4 Lorentz rotation, J1 and J2 combined in this way. And the D is the charge of the BPS state. And the M is the chemical potential associated with dynamic variables or the flavor masses. Okay. And then this JLJR, this chi is SU2 characters. Basically, here what is important is that this N, which is the degeneracy of the single particle BPS state, this, if we fix this, then we can get the compactified buffer invariance. Therefore, we get the OR partition function. So in followings, what I'm going to do is I'm going to determine this degeneracy using this blowup equation in a iterative way. So I will talk about what I mean by the iterative way in more detail soon. So another important thing that I mentioned is that as an input is a consistent magnetic flux. So it is magnetic flux on the P1, but which cannot be arbitrary. So it has to satisfy some quantization conditions. The quantization condition state in this way: the magnetic flux F couples to a BPS state, which is M2 braid wrapping a cycle, 2 cycle CI of the charge, a JLJR, should be quantized in the following way. And it should be integral or half integral when 2 times JL plus JR is even or odd. So if this is odd and we get the integer, the flux, and otherwise we get the half integer flux. So in terms of the gauge theory, so if we have a W bosons and dynamical this variable, then we give integral fluxes. For example, the W bosons are in the root, and the flux n takes these integers. As these are the root, so n is in the co-root lattice. One of the example is SUM case, and is given as it belongs to Z with this, and H is limited to here, and the different choice of n give rise to different fluxes. The hypermultiplied is a half integral flux, and this is the weight of the hypermultiplied. This is the background of fluxes that we can turn on. So basically, from this consistent magnetic flux condition, we can choose, and then we can put them as an input to solve when solving the blowup equations. So strategy is as follows. If theory is given, if theory that we are interested in, and then we have the geometry, and from geometry, and then we can have the input, effective prepotential and magnetic fluxes with this consistent magnetic flux conditions, and then we expand this partition function in terms of this scalar parameter, which is the exponential of the volume of two cycles. As I said earlier, for superconformal theories, all these volumes of the cycles is taken to be positive. So this expansion is well-defined expansion. So with this expanded partition function in our hand, we can solve the blow equation order by orders in this the scalar parameters. And along the way, we may not see that there may be some undetermined degeneracies, even though there is a undetermined the degeneracy, it can be another input for the not at the order that is not determined, but higher orders in the expansion. These can be play a role of the another input, and then we repeat the same procedure in this iterative way until we find the completely determined this undetermined degeneracies. And this is what our strategy that we are going to apply when solving the blow equation for any gauge series.
I have a question.
Yeah.
So is your method applicable for any gauge group, any matter content?
Yes.
Okay, I see.
Yeah, this is why I said this is a very powerful. The blow equation is very powerful. That you don't need the ADHN construction. You don't need to have the 5N web. You don't need to know others. Just a blow equation, and then also, of course, finding the proper input is also important. But with this input, you put on the machine. I mean, you just run iteratively, okay, and it will give you the BPS spectrum.
Okay, so all the information is this initial input.
Yes, I would say yes. Yeah.
Thank you.
But I didn't mention one thing, but I will talk about it later. But again, up to flux transitions. Okay.
Okay.
So yeah.
What about non-Lagrangian series?
So, okay, non-Lagrangian series. But if we have a geometry, we can still compute the effective potential. Also, we can turn on the magnetic flux. And then we again, and there is also the curve that we can take as a parameter of the expansion. And with this curve, with this scalar parameter, we can also solve the blow equation order by order. Another thing is that even in non-Lagrangian theory, it may be obtained by a decoupling of instantaneous hypermultiplet. And then we can actually check that the blow equation, with the geometry applying the blow equation, and the solution actually agrees with the gauge series description and then the RG flow of this instantaneous hypermultiplet. Actually, indeed, they do agree. Okay. So as an example, let me talk about the rank 1 and rank 2 theories. So here. Okay. So SU simplest gauge SU in 5 dimension, probably SU2, pure SU2. It has the discrete theta angle, two distinctive theta angle, known as theta equals 0 and theta equals pi. And their corresponding geometry is, as I said earlier, is F0 or F1. Or you can think of this one, if you're familiar with as a 5-brane web, and this is the zeta equals 0 5-brane web, and this is a zeta equal pi 5-brane web. And there are two basic cycles, which is base a curve and also fiber curve. And their volume is given as a 2 phi, which is this distance. And this distance for F0 is 2 phi plus m. M is the gauge coupling. And F1 cases, and you can see that this the volume of F is the same, but the volume of E is different. So this theory is basically perturbatively indistinguishable. So we expect that the perturbative part is the same, but as the base curve E are different, their instanton structure or instanton spectrums are different. Another example, for example, here if you are familiar with the structure, and this is a O-1 curve, and this allows a flood transition. After flood transition, this geometry looks like something like this. And then we can decouple this instantonic hypermultiplet and give rise to a local P2. Or F1 can be seen as the 1-point blow of the local P2. So here input is the effective prepotential. The effective prepotential is insensitive to discrete theta angle. So they are exactly the same. Here the M is the gauge coupling, and the phi is the Coulomb branch parameter. So, and then G perturbative is given as this. Again, P1, P2 is the e to the minus epsilon 1 and e to the minus epsilon 2. So up to here, these two theories share the same information. But the magnetic flux, actually, it distinguishes between them. So F1 case, so again, the vector, these W bosons are all integers, but the background fluxes, it turns out to be, is a difference, which is associated with this base curve. And the F0 case, it gives you a integer, and the F1, which is zeta equal pi, has half integers. This is because of the different structures, the spin structure arising this. So with this input, we can expand the blow equation to the first order of the e to the minus m, which is the instanton Kähler parameter. And then on the left-hand side, the right-hand side in the expansion give rise to this. Here, this background fluxes Bm comes as a parameter, and this is a one instanton partition function, the north pole, and this is one instanton partition function, the south pole. And basically, this equation has three unknowns: this and this and this. And then, as we discussed, we can choose the magnetic fluxes, at least, let's say, three distinct magnetic fluxes. That gives you three different, basically, equations. And then we have three unknowns, and with three equations, these actually solved completely. And not only actually this one instanton order, but all instanton order, and all of the form can be also obtained. And as an example, the solution of the one instanton expression is given this way for zeta equals 0 and zeta equals pi as this way and this way. So let me also say one more thing. Suppose that although we have the many possible magnetic fluxes that we can choose, suppose that we only choose one single magnetic fluxes. Can we still solve? So as a representative example, let me consider SU2 with the zeta equal 0. The Gobagua-Bapa invariant, the form takes this. Again, here this E is associated with the instanton and a Kähler parameter, and this is also associated with the Coulomb branch parameters. And here the goal is to determine this degeneracy. So this vector D, the appearing here, are basically the counting the degrees of the two cycles for E and F. For example, perturbative one means that this E shouldn't have no contribution, so it's a 0,1. I mean, as we already know, the perturbative, the form of partition function, it corresponds to the degeneracy of this 0,1/2 is simply 1. So to have one single blow equation, let me use that magnetic flux Bm to be 0. And then what we do is that as we discussed here, we first expand in terms of the scalar parameter of instanton, and then we further expand in terms of this D2, so Coulomb branch parameter. And then we will get the form of the blow equation. So then what we do is that we order by order solve the degeneracies. So these are the example. Here, this D is D1 is the instanton, so it's a one instanton cases. And then it turns out that we can fix with the D spins. Another spin that doesn't appear is over 0, but there we have a undetermined degeneracy n 0,1/2 and 1 the D2. So this is not fixed because this combination always appears in this form, and this is always canceled out. But at the one instanton. But if we go to the second order, then actually it can be fixed. And it is fixed as a 1 when the D2 is 0, and otherwise is a 0. So applying this, we can completely fix this BPS spectrum, which of course agrees with this. So this illustrates how we can solve the blow equation, although we do not have we may not have the three distinctive equations. And then this is the procedure of the iterative procedure. Let me go to rank 2 case. So SU3 with the Chern-Simons level K is less than 7. Geometrically, it is engineered by gluing two Hertzsprung surfaces, K+1, degree K+1, and F equal 1 or 0, depending on the Chern-Simons level is even or odd. So distinctive example is this. So SU3 with the Chern-Simons level 0 can be obtained by gluing two F1 Sorry. So SU3 with the chance-simul level 1 is obtained by gluing F1 and F2. So their volume is, for example, is given in this way, where these are basically the gartons, and then volume of E2 is for even and odd, it takes this following form. So here, again, the input is pretty much the same. So we have effective prepotential, can be easily evaluated. And the magnetic fluxes we can turn on is the N1, N2 is a vector. So it is integer. And then background fluxes, depending on the chance-simul level, we have the different choices. And with this Kopakuma invariant, Kopakuma buffer invariant form, we can determine the completely for, I think, the chance-simul level up to 3, we can have, I'm not sure it was 3 or 4, we can have more than 3 distinctive equation, so that we can have exact form for all other instantons. Well, even though we don't have, we can still find the BPS spectrum in perturbative, iterative way. So another example that I'm going to discuss is the as a duality. Is a representative example of the UV duality. The two theories have the same fixed point at the UV fixed point. And it is, in fact, can be seen as a base 5 duality. So it is SU3 with a chance-simul level 5 and SP2 with a discrete setup pi. Of course, you can also construct the five-band webs, and you can also see that these two five-band webs are actually do agree. Geometrically, these theories, in particular this SU3 theory with the chance-simul level 5, can be constructed this way. This tells you how to glue of the curve in the F1, F6. If I'm looking at the SU3 frame and the volumes of the curves are given as this way, if I look at the SP2 frame and the volumes are given this, but you will notice that these two are just the exchange of this, which can be understood as a 5-way dual. In fact, this the volume actually give rise to from this we can actually have the parameter map between two frames, and this is given this, which is also agrees with the 5-ring web constructions. Let me see. This also more explicitly checked by looking at the SP2 side. So SP2 effective prepotential is given this, when prepotential is also this, and then magnetic consistent magnetic flux is also given in this form. Here we have the 3 distinctive magnetic fluxes. So therefore we have 3 equations that actually give rise to the closed form of the instanton partition functions. And then we can check their duality by comparing the BPS spectrum of this. For example, here we already computed, we can compute, and SU3 with the 5, plugging in the blow equation, we obtain the spectrum, and to compare it to SP2, we're looking at the third component, which after base 5 dual, it becomes instanton part. And then collecting this term, we see exactly this state exists here. In this way, we can check the duality from this. Another interesting example is, of course, we can also do with, for example, SU3 with the Chern-Simons level 7, and also its dual theory, which is G2 theory, can be also considered this way, and duality can be also checked. There's another interesting theory is SU3 theory with the Chern-Simons level 8. Geometrically, it can be engineered in this way. So we have degree 9 portable surfaces and degree 1 F1. And there are 3 primitive curves. Unfortunately, this theory is rather strange. At the same time, it's interesting. In the UV limit, we see that these curves cannot be all positive or non-negative at the same time. So this means that the Coulomb consistent Coulomb branch cannot be obtained. Therefore, the theory does not have the UV completion in this geometric phase. But it turned out that it may be that it may have the UV completion. So it is pointed out that in the study of the 5D KK theory, so G2 with the one adjoint, the n equal 1 star theory, the Laksha he found that there's a dual theory, is SU3 with the Chern-Simons 15/2 plus 1 flavor. These are these dual theories. So from the SU3 side, here we have a 1 flavor. So decoupling of this 1 flavor, then it gives rise to a enhanced increment of the Chern-Simons level, which turns out which correspond to SU3 with 8. So this means that okay, so theory can exist. But interestingly, there has been lots of attempts, including myself, trying to find the fiber-in lab if there is, but it is still very challenging. And so far there is no ADHN constructions. So there has been any attempt to computing these partition functions for this. But I'm going to say that blowup formula can compute the partition function, and then I will talk about this. So as this SU3 with the Chern-Simons level 8, so we have an effective prepotential. Given in the same way, and this just applying the Chern-Simons level 8, and it turns out the magnetic flux that we can turn on takes this value. Okay, and then by plugging in this input, the BPS spectrum that we obtain is it's given here. But there is some state actually has a negative volume or negative masses, which is the state that I highlighted, which is the so this D vector is E2, which is the instanton part of this, and this D2, D3 is the degree associated with the 2 Coulomb branches. These 3 states turns out to be the negative masses. But at the one instant. What happened is that in this state turns out to be the spin is a 0, 0, which is hypermodified state, which allows the flux transitions. And then if we do the flux transition, and then we go to the non-trivial phase of the Coulomb branches, we are moving to the different chambers of the Coulomb branches. In there, we can obtain this SU3 with the tensor level 8 theories. Okay, so let me conclude. So the blow equation is, by the way, is there any questions?
So by the way, I have a question.
Yeah.
So for this so for this subset level 8, so how do you check that this is the correct spectrum? Do you have some other ways to verify it?
I think the no, there is no other computations. So after flux transition, we go to the state, a different state, and then we check their volumes, and then they all turns out to be positive.
Okay. Okay.
So in that way, we have the Coulomb branch. All the curves can be consistently not negative. So the theory exists.
So can I compare with result from 60? Because it comes from 60.
No, it doesn't come from. Oh yeah. Sorry. Yes. Okay, good. Thank you. Yes, we can compute this these two theories.
Right.
So we actually computed the SU3 theory with this 15/2 and 1 flavor, and then again decoupling this 1 flavor. We can also have the particle, I mean the BPS spectrum, and they do actually match this 1-to-1.
I see.
So this also agrees with the earlier proposal of how this SU3 should exist.
Okay, thank you.
Thank you for the question. So then let me summarize. The blow equation is very powerful equation that is an algebraic equation that partition function should satisfy. And then we claim that proper input, effective prepotentials, and consistent fluxes, we can actually bootstrap their BPS spectrum of the theories, and then by iteratively we can determine the BPS spectrums. So we go over some of the examples. Here I didn't mention the KK theory and 60 theories, but it is actually also we can apply, and we can also obtain. And there are many future directions. One of the things that we are preparing is introducing this Wilson line on this blow equation, and it seems to work very well. This codimension 4D effect can be also obtained in the blow equations. Okay, if I am done. If you have a question, please.
Thank you very much. Questions?
So you are suspecting SU3 tensor level 8 after flop is non-Lagrangian theory.
Yes, I think so.
So you are suspecting there's a consistent non-Lagrangian theory related, conformal free theory related to SU3 level 8. Okay.
Okay, so maybe I have another question. So given the theory, how do you determine the magnetic flux? So given just like some theory with matter, some Sung-Soo level. So how do you so do you do it by trial and error, or you have some way to
sorry, can you say again?
Yeah, I'm just wondering how to determine the magnetic flux.
This magnetic
given theory, right? Yeah, but for Sung-Soo level 8, you have like a 1 over 3, right? So this kind of flux.
Yes. We are here. Let's see. So in this way, you see that they should be integer, and then they are in the co-root lattice, and then they depending on the this h, you may have this fractional numbers.
So by the way, what is h? Sorry.
H is the what is the name? What is the name?
H is the center.
Center, yes, center of SUA. Taking the value from 0 to n.
SUN, yeah, center of SUN.
Yeah, center of SUN.
Okay. Yes.
Yeah, let me add a comment about the choice of the fluxes for the blobs. So here in this page, you know how to quantize the fluxes first. So by using our knowledge about the perturbative spectrum, for example, W bosons and hypermultiplets, by solving this quantization conditions, you will have some final list of the magnetic fluxes you can turn on. In addition, we need to turn on the background flux for the instanton symmetry. Question is how to determine the quantization condition for the instanton symmetry, because we don't know whether instanton has the spin kind of half or integer and so on. So depending on the spin for the instanton particles, the quantization condition for the instanton states or quantization conditions for the instanton symmetry will be determined. So for it, we have to first think about the general mode contribution for the instanton symmetry from the fields in the perturbative spectrum. Then by knowing such general mode contribution, we can anyway give some condition for the fluxes for the instanton symmetry, but we cannot determine whether it's integral or half integral. So we have to choose or we have to do some trial error for the instanton symmetry by knowing it would be integral or half integral. It gives anyway additional constraints for the instanton background magnetic flux. And moreover, we have to require the spectrum obtained from the blowup equation must include only the state with the non-negative volume. By combining these conditions, you will have only final list of the magnetic fluxes you can turn on. And we test all these final lists and find some consistent blowup equations for the spectrum of the given theory.
I see. Okay, thank you for your comment and thank you for the answer. Yeah.
Hi, I want to ask a question. Could you tell me more about this Wilson lines? Well, like, yeah.
I see. Okay, this is a not yet published. Let's see.
Or if you want, I can switch off the recording. I mean.
Okay, that'll be.
Okay, I will switch off.